Hello everyone, I'm pleased to present our work titled Collaborative Multi-Mode Pruning for Vision Language Models. Vision Language Models, or VLMs, have advanced rapidly within the unified transformer architecture, yet their deployment on resource-constrained devices remains challenging due to high computational complexity. While pruning has emerged as an effective technique for VLM acceleration, existing methods primarily focus on a single mode by pruning either parameters or tokens, suffering from severe performance degradation at high pruning ratios. Intuitively, parameter pruning and token pruning play complementary roles as they reduce the redundancy in model structure and input data, respectively. This motivates our investigation. Can joint pruning of both parameters and tokens achieve more effective compression of VLMs? However, this simple combination fails to unleash the potential of joint pruning, only achieving comparable performance compared to single-mode pruning. We attribute this to two core limitations. First, intrinsic inconsistency between parameter and token importance metrics. As observed in the figures, a large number of tokens to be pruned may still dominate parameter importance estimation, while token importance also highly relies on parameters that would be trimmed by parameter pruning. This may lead to suboptimal pruning decisions. Second, inflexible application of pruning modes. During progressive pruning, the optimal pruning mode, that is parameter or token pruning on the vision or language parameters, gradually shifts. Consequently, applying a fixed pruning order is prone to incur suboptimal solution, thus degrading the final performance under high pruning ratios. To address these issues, we propose COMP for VLMs by exploring effective simultaneous pruning of parameters and tokens. It consists of two key modules: collaborative importance metric and multi-mode pruning strategy. Overall, COMP adopts a nested optimization process to progressively reach the target flops budget, resulting in a static, structurally compact model with token pruning performed online during inference. In the CIM module, we reduce the interference between parameter and token redundancy during importance estimation. For parameter importance, we first extend the classical Wanda metric to structured pruning. Then, weight token-wise contribution via token importance, with stronger emphasis on the class token. Additionally, since token importance is directly determined by the MH computation in the current layer and the FFN in the previous layer, we explicitly distinguish the importance sources. For token importance, baseline metrics are usually derived from attention weights. However, parameter pruning masks directly applied to weight matrices may cause redundant heads to produce nearly uniform attention maps, which can dominate token importance estimation. To correct this, we move the parameter pruning mask to the attention map. In this way, the contribution of unimportant heads is gradually reduced to zero. In the MPS module, we decouple pruning into 5 modes and apply them alternately till the target flops. The pruning ratios of each mode is controlled by distinct importance thresholds. We also maintain a pruning cost, defined as the accuracy change per unit flops reduction. During optimization, MPS periodically selects the mode with the lowest pruning cost, increases its pruning ratio by adjusting the threshold, trains for several steps, and then re-estimates the cost. However, such process is locally greedy. To balance exploitation and exploration, we introduce random exploration with probability row. We also maintain a timestamp for each mode, which records how long since it was last executed. The longer a mode has been inactive, the higher its probability of being randomly selected. In addition, we update the pruning cost with an EMA-style estimate, where the influence of historical cost decreases as the time interval increases. This prevents outdated cost estimates from dominating future decisions. We conduct extensive experiments to validate the effectiveness of COMP. We apply methods to blip and clip models fine-tuned on visual reasoning, image text retrieval, and visual question answering tasks. COMP consistently outperforms both single-mode pruning and simple joint pruning baselines, with more pronounced gains under high pruning ratios. We further extend COMP to Lavity 1.57b, demonstrating its generalization capability to LLM-based VL-MIS. It also outperforms representative visual token pruning methods with only one epoch of fine-tuning. Ablation studies further confirm the contribution of each module. CHIM improves accuracy by mitigating the interference between the parameter and token importance estimation. MPS brings further gains by adaptively executing the pruning mode with higher current redundancy. We also evaluate practical inference efficiency on a single RTX 4090 GPU. COMP achieves up to 3.85 times speedup while maintaining SOTA accuracy. Finally, we visualize the mode shifts across progressive pruning stages. COMP exhibits more frequent mode shifting and explores diverse modes at different stages. Some necessary exploration steps contributes to recovery and ultimately leads to higher accuracy. The curve also reveals a clear trend that token pruning dominates early stages, while parameter pruning becomes more prominent in later stages. This indicates that input redundancy is easier to remove first, while structural redundancy becomes more critical as pruning proceeds. In conclusion, COMP enables more effective joint pruning for VL-MIS and further pushes the boundary of efficient model compression. Thank you for your attention, and feel free to visit our code repository.